Welcome to the Crazy Hat Chemist. So today we're going to do another video here, and this is going to be stoichiometry worksheet number 3. I'm going to make an assumption here, just like with all these videos, and this is the last one in this series. But the assumption here is the following. You have watched my YouTube videos on nomenclature. You know your periodic trends of ions and charges. You also know your ions and charges of polyatomic ions. So you're familiar with all the nomenclature. Then, number 2, you've watched my video series on chemical reactions and how to balance chemical reactions. And number 3, you've watched my video series on stoichiometry, of which this is. And there was an introductory stoichiometry worksheet. There was a stoichiometry worksheet number 1, stoichiometry worksheet number 2, and this is the final stoichiometry worksheet number 3. In addition to that, I'm assuming that you know a few other things or are familiar with a few other things for this. And number 1, you should be familiar with this flow chart right here. And that's going from mass to moles, from moles to molecules, from molecules to atoms, and atoms to molecules, molecules to moles, and moles to mass, as well as moles to volume at STP conditions. And then this up here is using the mole ratio. In addition to that, hopefully you have this periodic table right here. I'll be referencing this periodic table to come up with all the molar masses that are necessary on these problems here. All right, fantastic. So let's get started on this worksheet and let's see if we can knock this baby out. We've got, I think, 6 problems here to do. Not too bad. And try to break these up. If you do all these worksheets, you will have a very strong grasp of stoichiometry to move you forward in chemistry. All right, so here we go. We're going to start off with this first problem, and it says, number 1, if 0.75 grams of calcium nitrate reacts with ammonium chloride, what is the mass of nitrate product? What is the mass of nitrate product is produced? All right, so what we're going to do is we're going to find out what the formula for calcium nitrate is. So calcium is Ca, and it's a 2 plus because it's a group 2. Nitrate is a polyatomic ion of NO3 minus 1. Ammonium is the only polyatomic cation that you will more than likely be dealing with here at this introductory chemistry level. And then chloride is a halide ion, and that has a 1 minus charge. So you should see that this is going to be a double displacement, double replacement reaction. So I'm going to put these two together. What we do is we take the absolute value of these numbers, take the numbers, flip, and bring it down. I say take the bull by the horns, flip, bring it down, and you should get the following formula of CaNO3, parentheses, and a 2 outside. We're going to write down the state of matter. It's either a solid, liquid, gas, or aqueous, and all nitrate compounds are aqueous, no matter what they're with. Plus, ammonium chloride, and absolute value of these two numbers, flip and bring it down, and you should get NH4Cl. That's a 1-to-1 relationship. All ammonium ion compounds are also aqueous, so we'll just call that one as it is. Again, I think I'd mentioned this just a little bit ago, but this is a double displacement or double replacement reaction. So in order to write the products, I'm going to take this calcium and combine it with the other anion, that's chloride, and then I'm going to take the ammonium ion and combine it with the other anion, and that would be nitrate. It doesn't matter which of those two formulas that you write first on the product side, so long as their product formulas are correct. So we're going to do calcium chloride first. That's CaCl2, and that's a parentheses with that AQ right there. And this is aqueous because chlorides, bromides, and iodides are soluble. That's aqueous, except for silver, mercurous, and plumbus, of which calcium is not any one of those 3. Then we have ammonium nitrate, and then we have, that would be NH4NO3. And all nitrate compounds are aqueous, so that's going to be aqueous. Now what we need to do is balance this for charge and mass. And for mass, we got a 2 chloride here. We got 1 here. So 2 chlorides on the product side, 1 on the reactant side. I'm going to place a 2 in front of the ammonium chloride. Now I have 2 ammonium ions or 2 nitrate ions, and that would cover that with having a 2 in front of the ammonium nitrate. Perfect. All right, now what we're going to do is we're going to start off with the number units formula, of which we have in this problem, and it says that we have 0.75 grams of calcium nitrate. So I'm going to write that down, 0.75 grams of calcium nitrate. Okay, so let's think. Hopefully that is looking good for you. Okay, so here we go. We're going to continue with this, and we got our 0.75 grams of calcium nitrate, and then we're going to kind of draw a line here so that we can do our stoichiometry and make it nice and clear. All right, one of the things that we're going to look at is this a limiting reagent problem? And since there is only one number of one compound, it's not a limiting reagent, so that's really nice. So what we need to do is we are going to do our stoichiometry. What we want to do is we want to cancel out the grams of calcium nitrate. In order to do that, I need to have grams of calcium nitrate here down in the denominator for the units and the formula. All right, so I have done just that. And then I'm going to look at my flow chart. And so I'm looking at my flow chart. I'm going from a mass to moles, and then the conversion is the molar mass. This moles tells me what the units are in the numerator, and the number that's associated with that is an 1. So we're going to write that down. So it's going to be 1 mole of said same formula, calcium nitrate. Okay, and the conversion from moles to mass or mass to moles is using the molar mass. And so what we're going to do is we're going to find calcium on our periodic table, and it has a molar mass of 40.08. And we're going to find nitrogen on our periodic table. It has a molar mass of 14.007. We're going to multiply that by 2. And then we are going to have oxygen's molar mass, and that is 16.00. And we're going to multiply that by 6. And so then we're going to get the molar mass, and that is going to be 164.09. And that has been rounded to 2 decimal places because the fewest number of decimal places in calcium, nitrogen, and oxygen is 2. Okay, now that we got the molar mass for calcium nitrate, and again, just to reiterate, we have rounded this number to 2 decimal places because calcium has 2 decimal places, nitrogen has 3, and oxygen has 3, and the fewest number of decimal places is what we're looking at. So we're going to be able to cancel out the grams of calcium nitrate just like that. Now, what we want to do is we want to go, it says, what is the mass of nitrate product? So I need to find the nitrate product. What is the nitrate product? It is right here with ammonium nitrate. Now, I just want to make sure that you understand that the products are calcium chloride and ammonium nitrate. So I'm choosing this one, ammonium nitrate, because it is a product that has nitrate in it. But I'm not just looking for nitrate. I'm looking for the whole product that has nitrate in it. Okay. All right, so our next step here is to cancel out the units of moles and the formula of calcium nitrate. So that's going to be moles of calcium nitrate right down here in the denominator, like thus. And then I'm going to go to moles of whatever I want in this balanced equation. And so that will be moles of ammonium nitrate, just like this. And I'm going to use the stoichiometric coefficients from the balanced equation, and it's a 2 in front of the ammonium nitrate, so that's why this is a 2, and a 1, it's an assumed 1 in front of the calcium nitrate, and that goes right there. So we have a little bit more to do, so I need to continue on my monorail here just a little bit and draw a line. Okay, and this enables me to cancel out the moles of calcium nitrate just like that. Now what we're going to do is we're going to have these units and formula. That's moles of ammonium nitrate. That will be moles of ammonium nitrate. right down here in the denominator term. And then we need to go from moles to grams. And again, if we have out our flow chart and we understand what's going on, we are going from moles to grams. All right. And what do we use? The molar mass. Perfect. So that's going to be grams of ammonium nitrate. And again, this will enable us to cancel out moles of ammonium nitrate like that. Okay, this number right here is a giant 1 because 1 mole is equal to the molar mass. And so what we're going to do is we're going to peel off our periodic table here, like what we did earlier here. And I think, yep, that's what we have. So ammonium nitrate, we're going to look at hydrogen. And we're going to take the molar mass of hydrogen, 1.0079, multiply that by 4. Then the molar mass of nitrogen, and that's 14.007, multiply that by 2. And then the molar mass for oxygen, that's 16.00, and multiply that by 3. Now, we have 4 decimal places, 3 decimal places, and 2 decimal places. So our molar mass for ammonium nitrate is going to have the fewest number of decimal places, which is going to be 2, because that is what oxygen has. So I'm going to have 80.05. And then I'm going to make one other comment here, and that will be a comment with every single molar mass calculation. You are going to, once you've done the molar mass calculation, you've written it down, then what I want you to do is use a whole number molar mass calculation in addition to that. So the formula for ammonium nitrate is NH4NO3. So what you're going to do is you're going to say hydrogen times 4. And I'm going to use a whole number. Then nitrogen, that's 14 times 2. And then oxygen, 16 times 3. I'm going to sum those up. I'm going to get a whole number. And that whole number is 80. And that's why I'm going to say I'm going to assume that I have calculated this molar mass correctly. All right. Now we're going to look at significant figures in this problem. This is 2 significant figures. This is an infinite number of significant figures. This is 5 significant figures. Infinite, 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 and 4 significant figures. So the fewest number of significant figures I have on this problem is 2. So I'm going to take 0.75 divided by 164.09 times 2 times 80.05, and then round that number to 2 significant figures. I'm going to have 0.73 grams of ammonium nitrate. And this is going to be my final rounded answer. It has 2 significant figures. It has number, units, and a formula. That's number, units, formula. Don't forget about that for every single answer, for every single problem. You need NUF. That is number, units, formula. All right. Coolio. Let's move on to problem number 2 of this same worksheet. So I'm going to slide this baby up here just a little bit so you can see it all. And there we go. All right. Again, just a quick little reminder, you are watching the Crazy Hat Chemist. Please watch my videos on YouTube, and please subscribe to my YouTube channel and encourage all your friends, your neighbors, your coworkers, your colleagues in school. Spread the word that this is the place that you go to get all your chemistry answers. All right, fantastic. So let's move on to this next problem. And this next problem says magnesium metal. So magnesium is an element. And since it is a metal, it is a solid at room temperature and pressure. Okay. And then it says hydro, root word chlor, and then ic, acid. So that is a binary nonmetal acid, and that's a hydrogen plus a chloride ion, and that would be HCl, and that is most certainly aqueous. Okay, this is a single displacement type of reaction. And how do I know that? I have an element and a California. That is a cation-anion combination. This magnesium is going to, since it is a metal, and forms cations, it will displace either a metal or a cation, and the hydrogen is the cation. So what you will end up having is the hydrogen will be displaced, and then hydrogen will now be the element that is all by itself. Hydrogen, when it is by itself, it is one of the 7 famous diatomics, so it will be H2 because it's diatomic. Hydrogen, in its standard conditions, is a gas, so that's why that's a G right there for that. And then I'm going to get the magnesium ion with the chloride ion, and those two will be combined together. So magnesium, when it is not a metal, is group 2, and it is a +2. And we already know the charge on the chloride ion, so we're going to combine those two things together like this, MgCl2. And this is also going to be aqueous because chlorides, bromides, and iodides are soluble except for mercurous, plumbus, and silver. So that's not one of them. So now what we need to do is balance this equation. There are 2 chlorines and 2 hydrogens on the product side and only one of each of those on the reactant side. So I'm going to place a single 2 right there in front of the hydrochloric acid, and then my balancing is done. Okay, all right. Now we're going to move on to the stoichiometry portion of it. It says that 1.75 mils of hydrochloric acid with a density of 1.13 grams per mil is what we have. And then it says how many grams of gaseous product is formed. So that's what we're looking to form and solve for. So we're first going to start off with this 1.7 milliliters of HCl. So 1.7 mils of HCl. All right, and then what we're going to do is draw our line here in the sand so that we can carry on with this problem. This is probably going to be a pretty long line here. Okay, and then we'll do this vertical stop here. Okay, all right, just like that. Now, so I'm going to ask you, as we have done with many problems, we have canceled out units, and that's what we're doing here as well. So we're going to cancel out units. These are milliliters of HCl, and so therefore I'm going to have milliliters of HCl down in the denominator right there. Okay, and then we'll do our vertical stop as well. So, and this will enable me to cancel out the milliliters of HCl. Okay, now, question, do you go from milliliters and use this 22.414? The answer is absolutely not, because there is nothing in this problem that says it's at STP conditions. This 1 mole to 22.414 only occurs at STP conditions, and this is not at STP conditions, so that's a no, absolutely no. What we are going to use is the density that was given, and that is 1.13 grams of HCl per milliliter, and that would be 1. So now we should be kind of like conceptually home free in that we are almost starting off with grams of HCl instead of a volume now. And again, since this is not at STP, I'm not using 22.414. And what I mean by that we should be home free is that we are going to be canceling out the grams of HCl. So therefore, grams of HCl will be down here in the denominator. I'm going to draw my stop here for this vertical stop for the next term. So now I have grams. So I'm going to go from grams, that's a mass, to moles. It tells me what goes in the numerator and what do I use as a conversion, the molar mass. So I'm going to go to moles, and it's HCl, and it's a 1 mole, and then I need to calculate the molar mass. So hydrochloric acid is hydrogen, that's 1.0079, and chlorine, that's 35.453. Hydrogen has 4 decimals. Chlorine has 3 decimals. So the fewest number of decimals is 3, and that final rounded answer with 1 hydrogen and 1 chlorine is going to be 36.461. Again, to 3 decimal places. That enables me to cancel out the grams of HCl. Now, then I'm going to reread the question here, and it says how many grams of gaseous product is formed. So I'm going to look at the 2 products. Which one is a gas? It's right there. So I am going to mass of this gaseous product. So in order for me to cancel out these moles of HCl, I'm going to have moles of HCl right here in the denominator, my vertical stop, like thus. And then I'm going to have moles of whatever it is that I want, and that's going to be H2. And then what we're going to do is we're going to use our stoichiometric coefficients from our balance equation. The number in front of the HCl is a 2, so that's why this is a 2. The number in front of the hydrogen is an assumed 1. That's why that is a 1. Now I can cancel out the moles of HCl. And we are almost there. We have only one more thing to do. And so we're going to go over here. We have moles. We want mass. We're going to be using the molar mass. So moles of H2 go in the denominator. And how many moles? 1 mole, because of this 1 mole is equal to the molar mass. Okay, and then we're going to have grams of HCl, and that's going to be 1.0079 times 2. That's 2.0158 grams of H2. This enables me to cancel out the moles of H2. I'm going to be looking at my significant figures, and I have 2 significant figures, 3 significant figures, infinite significant figures, 5 significant figures, infinite, 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 and 5 significant figures. So the fewest number of significant figures I have on this problem are 2. So in my calculator, I'm going to plug in the following numbers in the following way. 1.7 times 1.13 divided by 36.46 divided by 2 times 2.0158. I'm going to round that answer to 2 significant figures, and that is 0.053, and that's units of grams and the formula of H2. I just want to also make sure that you understand this, and that is you can write another possible answer, and you can put it in exponential notation, which would be 5.3 times 10 to the negative, because this number is less than 1, 2. And I would have the same units, that's grams, and the same formula of H2. So this is an or statement. I recommend that you do not put or statements, but I'm just showing you that you can either have the number in decimal form, as on the left, or in exponential notation, as here on the right. And you can never go wrong with exponential notation. Exponential notation will always get you the correct answer all the time. All right? Okay. So now what we're going to do is we're going to give problem number 3 a try. So we're going to slide this on up and see what we got. And here we go. Fantastic. All right. Before we start number 3, again, just remember, I am the Crazy Hat Chemist. You're watching a Crazy Hat video right here. Just absolutely crazy. I know we're going bonkers over here doing chemistry problems, but it's the fun stuff, most certainly. And please watch my YouTube videos, subscribe to my YouTube channel, and I love you, and I'll see you soon. So here we go. This next problem has phosphoric acid. That is coming from the phosphate ion, which is PO4 3 minus. And all acids have hydrogen, so that's hydrogen like that. Okay, and then sodium metal. Sodium metal is Na. All right, so we're going to find out what happens on this one, and we're going to write H3PO4, that's aqueous because it's an acid, plus Na, and that's a solid because it's an element in its standard conditions. And what type of reaction is this? This is a single displacement reaction, just like the last one. And that is, I see an element right here in sodium, and I see a California. This element of sodium is going to displace the hydrogen, and then you're going to get hydrogen on the product side. That will be H2, and that's an element in its standard condition. It is diatomic, and that will be a gas. Plus, and then I am going to combine the sodium ion, which is a group 1 cation, with the phosphate, and that will be Na3PO4, Anything with sodium is aqueous, so that's why this is aqueous. So hopefully you understood that single displacement reaction where the sodium is displacing the hydrogen. Notice that this is H2 and there are 3 hydrogens over there. Okay. Now what we need to do is balance this beast. So here's what we're going to do. We're going to say, let's look at the hydrogens. I have 3 hydrogens on the reactant side and 2 on the product side. So we're going to find the greatest common factor, which is 6. So that would be 3 in front of the hydrogen and then 2 in front of the phosphoric acid. Then I can also notice that there are 3 sodiums on the product side and only 1 sodium over here. Okay, but also I just put a 2 in front of the phosphoric acid. So there's a 2 in front of the phosphorus. So I'm going to have to put a 2 in front of that phosphorus like that. Now I should say that there are 2 times 3, that's 6 sodium. So I'm going to have 6 right there in front of the sodium. Right? Hopefully that's working out okay for you. So now I'm going to start off with number units formula, and the number of which I have on this problem is 1.87. The units for this is grams, and the formula is the Na for sodium metal. Okay, so we're going to start off with this on our problem, and we're going to go draw our vertical stop line in between our next section. Okay, and then so if this is grams of Na, I want to cancel that out. So I'm going to have grams of Na right down here. And then I'm going to look at my flow chart and I'm going from mass, that's grams, to moles. So I'm going to have moles up here in the numerator of Na, and the number is a 1. Number is a 1 because of my flow chart, just to verify and validate that. I'm going from mass to moles. The number in front of the mole is a 1, and I'm using the molar mass to toggle back and forth between them. Now I need to look on my periodic table to find the molar mass of sodium, and here it is right here. There's sodium, and it's 22.99. I don't have to multiply it or add it to anything else. I use the same number of decimal places that are right there because it's just the molar mass of that element. Grams of sodium cancels out. All right. Perfect. Now we're going to do our next step right over here, and then in order to cancel out the moles of sodium, I'm going to have moles of sodium down here in the denominator. Okay. Now what we're going to do is read what the question says, and it says how many grams of gaseous product is formed. So I'm going to look at the 2 products. Which one is a gas? There's our gas, so I'm going to go to that. So this is the time that you can change the formula, is when you have a mole ratio. So really important. When you have a mole ratio, you can change the formula. So this will be H2. I'm using the stoichiometric coefficients from the balanced equation. That's a 3 in front of the hydrogen and a 6 in front of the sodium. And then we're going to put our vertical stop in between this here and our next term. This enables us to cancel out the moles of sodium. Then we have one more thing to do, and we are going to now take this to grams of that gaseous product. So I'm going to have moles of H2 down here in the denominator. How many moles? It's going to be 1. Why is it 1 mole? Because I'm right here going from moles to mass using the molar mass. And then I'm going to have up here grams of H2 in the numerator. So I'm going to pull out my periodic table. I'm going to find hydrogen, and it is 1.0079. I'm going to multiply that number by 2, and I'm going to get, just like I actually had on the last problem, that will be 2.0158. That's the molar mass for hydrogen. I'm going to cancel out the moles of H2. I'm going to have 3 significant figures. Infinite number of significant, 4 significant figures, infinite number of significant figures, infinite number of significant figures, infinite number of significant figures, 5 significant figures. So the fewest number of significant figures I have is 3 on this problem. So I'm going to type into my calculator the following way and the following numbers: 1.87 divided by 22.99. Divided by 6 times 3 times 2.0158. Notice that I skipped the ones here. Then I'm going to get a number in my calculator. That's going to be 0.0820. I'm going to have units of grams, the formula of H2. I'm going to write an OR statement on this one as well. And I can, if you want to, put this in exponential notation. This number here is in decimal notation. Notice it has 3 significant figures. The leading zeros don't count, they are placeholders. So 1, 2, 3 significant figures. That's a trailing zero with a decimal in it. It counts as a significant figure. Alternatively, I can have this in exponential notation, and this would be the number. If I move the decimal 1, 2 places, the number is less than 10, less than 1, so it's a negative and a 2, and that's grams of H2. So it doesn't really matter. I have number, units, formula. I have rounded it correctly with the number of significant figures, okay? Hopefully you're okie dokie with that. All right, so we are done with these first 3 problems. Now what we're going to do is we're going to do the next problem. That's number 4. So peel this away and out number 4 out of the woodwork, so to speak. Right? I mean, there's a table. It's made out of wood, so there must be some woodwork right here. All right, so here we go. Problem number 4. Before we get started on this, just a quick little reminder. You watching The Crazy Hat Chemist? That's right, folks. The Crazy Hat Chemist. Find me on YouTube. You're probably watching this on YouTube, but find all my other videos on YouTube. I got some great videos on YouTube to give you a foundational material of all this stuff. All right, so let's get moving on this. We got a 0.34 grams of xylene, that's C8H10, is poured. So that's letting us know that this is a liquid. Okay. Into a petri dish and lit with a match. Lit with a match lets us know the type of reaction. So hopefully if we write down the reactants, then we can come up with the type of reaction of which this is. Okay. And so here we go. It's C8H10. It's a liquid. It says it's lit with a match. That means it's going to be on fire. Therefore, this is a combustion type of reaction. So I'm going to have plus O2. That's a gas. I'm going to have an arrow. There's going to be a delta above the arrow, so that's necessary. And then this is going to be a complete combustion. And so we're going to have carbon dioxide, that's a gas, and water, H2O, and that's a liquid. Then what we need to do is balance this problem. And so how we balance any combustion reaction, we balance starting with the carbons, that's going to be 8. Then balancing with the hydrogens, there's 10 hydrogens on the reactant side, so I'm going to have to multiply this water by 2. We're going to sum up these number of oxygens, that's 8 times 2, that is 16. Then plus 5 times 1, that's 5. I'm going to add these 2 numbers up right here, and that's going to give me what number? That's 21. I'm going to look at, on this compound here, there are no oxygens right over here. So that means I'm going to use a fractional coefficient of 21/2. Now, officially, this equation is balanced, but one of the things that we do at this stage in our chemistry instruction is that one of the rules is we cannot have fractional coefficients. So therefore, since we cannot have fractional coefficients, we're going to multiply the entire equation by this denominator 2 to get rid of that 2 to get rid of the fraction. So my ending coefficients are going to be 2, 21, 16, and 10. Now I have my balanced equation. All right, cool. All right, so now what we're going to do is we're going to find the number of which we have, and it has 0.34 grams of xylene. And then it says there is 0.42 grams of gaseous reactant. Oh my. So this is what we're going to do. I'm going to say 0.34 grams of that xylene, and then 0.42 grams of the other gaseous reactant. That's right there. And it says how many liters of gas is produced at STP, what is the limiting reagent, and what is in excess. Oh my gosh. So what, how many liters of gaseous product? So of the two products, which one's a gas? Right here. So that means I need to take this to carbon dioxide. Notice that this is a limiting reagent problem. And how do I know that? I have a number for both reactants. That identifies this as a limiting reagent problem. Okay, so now what we're going to do is we are going to work on doing the math associated with this because this has just a little bit more steps than if it were not a limiting reagent problem. All right. All right, now that we have characterized this reaction as a limiting reagent problem, so let's carry on with this and see what we can do with those numbers. Again, it's a limiting reagent problem because I have numbers for both of the reactants. So I'm going to take this 0.34 grams of xylene, that's C8H10, and I'm going to start with that one. And let's draw our little monorail here. Oops. There we go. All right. And here's my vertical stop. All right. All right. So let's move this up a little bit here. Maybe we can fit this all in here. So this is grams of C8H10. And so therefore, I'm going to have grams of C8H10 over here. So grams of C8H10. And using our flow chart, we're going from mass to moles. We have 1 mole that's going to be in the numerator. So this is going to be 1 mole of the same formula, C8H10. And then here is our vertical stop. Fantastic. All right. Now what we need to do is we need to calculate the molar mass, because we're going from mass to moles. We need to calculate the molar mass of the xylene, that's the C8H10. And so we're going to be looking at the hydrogen, that's 1.0079. And we are going to be looking at the carbon, and that's 12.011. There are 4 decimal places in hydrogen, and there are 3 in carbon. So I'm going to have the fewest number of decimal places. That will be 3. So I'm going to say 8 times 12.011 plus 10 times 1.0079. And so that will lead 106.167. And those are the grams. That will enable me to cancel out grams of C8H10, and then I'm going to keep on going with this here. So this is moles of C8H10. I'm going to have moles of C8H10 down here in the denominator, and I'm going to go to moles of whatever I want. And it says that I want to get to the gaseous product, and we already identified that as carbon dioxide. So we're going to say moles of carbon dioxide. Vertical stop. And then we're going to use the stoichiometric coefficients from the balanced equation. In front of the carbon dioxide is a 16. In front of the xylene is a 2. And then it says that we want to get 2 liters of gaseous product. So this enables us to cancel out moles of the xylene. So we're going to have moles of CO2. And then we're going to use our flow chart right here. And so we are here at moles. We used our mole ratio, and we're here at moles, and we're going to go to a volume of a gas at STP conditions, and that's 22.414 liters is equal to 1 mole. So 1 mole, 22.414 liters of CO2. And that's going to cancel out the moles of CO2. I'm going to get a number for this here in just a little bit. Okay, but before I do that, I'm actually going to do the next step here in my stoichiometry, and I'm going to start off with the 0.42 grams of the other reactant, the gaseous reactant, which is O2. So we're going to start off with that. That's 0.42 grams of O2. And my vertical stop and my continuation of my problem here. Okay, fantastic. So I think we're going to be able to get this all in. And so we have 0.42 grams of O2. And so therefore down here in the denominator goes grams of O2. And we are going to use our flowchart. We're going from grams to moles, and we're using the molar mass. And so we're going to have moles of O2, and that's 1 mole, and then we're going to use the molar mass for oxygen. On the periodic table, oxygen is 16.00. I'm going to multiply that by 2, and therefore that will be 32.00. Notice that I did add the 0.00 because oxygen is 16.00 on the periodic table. So this does need to have 2 decimal places with it. Vertical stop in between the two here. This enables me to cancel out grams of O2. Now I have moles of O2, and we're going to move this up here just a little bit. And we're going to say moles of O2, and I'm going to go to moles of anything that I want. And it does say that I want to go to liters of the gaseous product. So I'm going to go to moles of the gaseous product, which is carbon dioxide. I'm going to have my vertical stop right here. And then I'm going to use the stoichiometric coefficients from the balanced equation. In front of carbon dioxide is a 16. In front of the oxygen is a 21. All right. And then we're going to cancel out our moles of O2. And again, what we want to do is we want to end with the liters of the gaseous product, and therefore we're going to cancel out these moles of CO2. We're going to have moles of CO2 right here. That number is going to be a 1. I'm going to be able to cancel out my moles of CO2, and I'm going to go from moles of CO2 to 22.414 liters of CO2. Awesome. All right, so now what we're going to do is we're going to pull out our calculator, and we're going to take a 0.34 divided by 106.167 times 16 divided by 2 times 22.414. And I'm going to round this to the fewest number of significant figures. 2 significant figures, infinite, 6, infinite, infinite, 5, and infinite. So the fewest number of significant figures is 2 significant figures. And so again, I'm going to take 0.34 divided by 106.167 times 16 divided by 2 times 22.414. And I'm going to get the number 0.57, and that's liters of CO2. And so that's one of my numbers. I have 2 significant figures here, infinite number of significant figures, 4 significant figures, infinite, 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 and 5. I'm going to plug into my calculator 0.42 divided by 32 times 16 divided by 21 times 22.414. I'm going to round that number to 2 significant figures. That's 0.22 liters of CO2. Right? So now what we're going to do is we're going to compare these 2 numbers. This is the beautiful thing about a limiting reagent problem, is that we have the ability to compare the numbers when we have numbers, units of the same units and the same formula. Now I can compare the numbers. So what we're going to do is we're going to compare the 2 numbers. We're going to find the smallest number. This is going to be the amount of carbon dioxide or gaseous product that can be produced. I'm going to cross out the larger one. So I'm always picking the smaller number. In order to figure out what the limiting reagent is, I'm going to take this smaller number and find out what made it. What made it is O2. So the limiting reagent is O2. Okay, and then the number that could have potentially made more, but I crossed it out, the one that one was, is C8H10, and that is the compound in excess. Okay, so now I have answered all my questions here. How much gaseous product can be produced? That's 0.22 liters of CO2. What's the limiting reagent? O2. What's the compound in excess? And that is C8H10, and that's the xylene. Okay, fantastic. So this problem is done. We're going to peel this awesome problem away, and we are going to move on to our next problem. So that's number 4. Number 4 is down. We're going to hit upon number 5. Again, while I shift my papers here, quick little advertisement. You are watching The Crazy Hat Chemist. Please watch more of my videos, subscribe to my YouTube channel, and get all your chemistry answers answered. Okay, here we go. Next problem here. It says a solution containing ferric chloride. Ferric is Fe3 plus, chloride is Cl1 minus, is mixed with a solution containing sodium oxide. Sodium is 1 plus because it's a group 1. Oxide is a 2 minus. That is a periodic trend charge. So I'm going to have FeCl3. That's a solution. That's AQ, and then Na2O, and that's also a solution. Chlorides, bromides, and iodides are soluble except for silver, mercury, and lead, and all sodiums are soluble, so that's not a problem. This is a double displacement, double replacement reaction. The iron is going to get together with the oxide, and the sodium is going to get together with the chloride. So I'm going to write that sodium chloride first, not that it mattered. And this is going to be aqueous plus the ferric oxide. And so that's going to be Fe2O3. And from solubility rules, that lets us know that that's a solid. That is, oxides are insoluble except for group 1 and ammonium ion. Now, what we're going to do is we're going to balance this. And most commonly, you look at the most complicated formula and look for balancing. This is the most complicated, unusual formula. So there are 3 irons here. There's 1 here. So, sorry, excuse me. 2 irons on the product side. There's 1 iron on the reactant side. I'm going to place a 2 in front of the ferric chloride. There are 3 oxygens on the product side. There's 1 oxygen on the reactant side. I'm going to place a 3 in front of the sodium oxide. That gives us 3 times 2, that's 6 sodiums, and 2 times 3, that's 6 chlorides, and therefore I'm going to have that number in front of the chloride. All right, well, we have a lot of information here on this problem and a lot to do on this problem in addition. So this is a limiting reagent problem. And why do I know that? It's because I have 0.378 grams of the ferric chloride is mixed with the 0.156 grams of the sodium oxide. And then it says, how many grams of oxide product is formed? That's the oxide product. What is the limiting reagent? What reagent is in excess? And what is the percent yield if 0.065 grams of the oxide product was measured in the lab? How many grams of unreacted reactant remain? Right. So just to make sure that you've got everything that you need on this one, and as far as concept, if you have numbers for both reactants, that tells you it's a limiting reagent problem. If you have a number for one of the products, of which we do, that tells you that I need to take both of these numbers to this product, especially if I have a percent yield. So this will tell me the percent yield. And this is going to be, since it's the given value, this is the actual. This is the actual value, the given value of my percent yield. All right. So let's start this problem off here and see how far we can get with this very successfully, I will hopefully say. So we're going to write a little bit smaller because I got a lot of information to write on this problem. So we're going to start off with 0.378 grams of the ferric chloride. All right. I'm hoping that you have a periodic table with you and you're familiar with the formulas on the periodic table and their molar masses. So I'm going to assume that you know that by now, especially since this is the 3rd worksheet. But I do have iron on my periodic table, and that's 55.85. And I also have chloride, and that's 35.453. Iron has 2 decimals. Chlorine has 3. So I'm going to have 2 decimals for my ferric chloride. That is, I'm going to multiply the molar mass of the iron by 1, the molar mass of the chloride by 3, sum them up, and round it to 2 decimal places. So that's going to be 162.21 grams of ferric chloride. This will enable me to go to moles of ferric chloride, and I'm going to have 1 mole of that ferric chloride compound. I'm going to write my vertical stop in between this and my next step so that I can clearly see them. My units of grams of ferric chloride cancels out. I'm going to have moles of ferric chloride now, and I'm going to go to moles of whatever it is that I want. And what is it that I want? I want to go to moles of the ferric oxide. So moles of ferric oxide. Again, another really good reminder here, and that is the only time you can change formulas, of which I have done here, is through a mole ratio. This is a mole ratio, and I'm using the stoichiometric coefficients from the balanced equation. That for ferric chloride is 2. That for the iron oxide, the ferric oxide, is a 1. I am trying to get a mass, so I'm going to, I am going to cancel out moles of the ferric chloride. Since I'm trying to get a mass, I'm going to say I'm going to have 1 mole of now this ferric oxide. Remember, the molar mass for iron had 2 decimal places. The molar mass for oxygen has 2. So I'm going to multiply the molar mass of iron by 2, the molar mass of oxygen by 3. I'm going to round that to 2 decimal places. That will be 159.70 and then grams of Fe2O3. This will enable me to cancel out moles of the ferric oxide. I'm going to look at significant figures here on this problem, and I have 3 significant figures: 5, infinite, 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 and 5. So the fewest number of significant figures I have on this are 3 significant figures. In my calculator, I'm going to plug in the following numbers in the following ways. That's 0.378 divided by 162.21 divided by 2 times 159.70. Now I'm going to round that number to 3 significant figures. That will be 0.186. The units are grams. The formula is ferric oxide. And this is one of my potential answers here. All right, fantastic. We're going to do the next one of our limiting reagent problem. And so we have 0.156 grams of the other reactant, which is the sodium oxide. So we'll start off with that, 0.156 grams of the sodium oxide. Again, we'll draw our line in the sand here, and that will enable me to do my vertical stop here between this and the next step. And we have grams of sodium oxide right here in the numerator. Therefore, I'm going to have grams of sodium oxide in the denominator. I'm going to find my periodic table and find sodium 22.99, multiply that by 2. Oxygen, 16.00, multiply that by 1, sum them up, and I'm going to have 2 decimal places because both sodium and oxygen each have 2 decimal places. So I'm going to have 61.98 grams of Na2O, and that will be equal to 1 mole of Na2O. I'm going to have my vertical stop in between these. I'm going to cancel out grams of sodium oxide. I'm going to go from moles of sodium oxide to moles of the ferric oxide. And my vertical stop. And I'm going to use the stoichiometric coefficients from the balanced equation. That for sodium oxide is a 3. And that for the ferric oxide is a 1. I'm ultimately going to the end same thing. Okay, I'm going to have cancel out the moles of sodium oxide. That's Na2. There we go. And then I'm going to have moles of ferric oxide. And then I already calculated the molar mass of the ferric oxide previously, so I don't have to recalculate it. It's right up here. That's 159.70 grams of Fe2O3. I'm going to cancel out the moles of ferric oxide. This is going to equal a number. I'm going to look at significant figures. This is 3 significant figures: infinite, 4, infinite, infinite, 5, and infinite. So the fewest number of significant figures, just like on the previous one, is actually 3. So I'm going to have 0. Oh, wait, I'm going to plug this into my calculator first. That's 0.156 divided by 61.98 divided by 3 times 159.70. So the number I'm going to get in my calculator is 0.134 units are grams, same formula of Fe2O3. So that's 0.134. I'm going to circle that. All right, fantastic. Now I'm going to be able to answer many questions just from the information of which I have right here now. Okay, so number one, I can compare these two numbers because they have the same units, that's grams, and the same formula, Fe2O3, that's ferric oxide. I'm going to look at these two and I'm going to find the smallest number. The smallest number is the amount of product that can be produced of the ferric oxide. This is my theoretical value. And then I am going to cross out the one that's in a larger number. So there we go, crossing that one out. Okay. This also enables me to answer which one is the limiting reagent. The smaller number, the one that made that, is the limiting reagent. So what's the limiting reagent? Na2O. And the other one that I crossed out, that other reactant, is in XS. So FeCl3 is in excess. So how much ferric oxide can be produced? 0.134 grams. That's right here. What is the limiting reagent? I'm using this smallest number to figure out the limiting reagent formula of Na2O. What is the formula in excess? That's the one that I crossed out, and I'm going to come back to that other reactant. That's FeCl3. Notice that when I identified the limiting reagent and the one in excess, they must be reactants. If they are not reactants, it ain't correct. All right, good on that so far. Just think about that. Okay, so now what we're going to do is we're going to do the next simple step. And the next simple step is actually to determine the percent yield. So the percent yield is going to be the actual over the theoretical. And since I want a percentage, I'm going to actually multiply that by 100. So the actual is always given within the problem, and that was 0.065 grams of Fe2O3. The theoretical amount was 0.134 grams Fe2O3, and I'm going to multiply this by 100. Okay. So just to make sure, the actual is the number on the top. That is the number that's given in the problem. The theoretical is the number on the bottom. That's calculated. Theoretical is always calculated. This has two decimal places, or sorry, two significant figures. This has three significant figures, infinite number of significant figures in the 100 there. So I'm going to take 0.065 divided by 0.134 times 100, round that to two significant figures, and I'm going to have 49% yield of Fe2O3. And that is my percent yield. All right, fantastic. Now what we're going to do is we're going to do the very, very last step of this problem and figure out how much of the reactant that is in excess, which one is in excess, FeCl3, how much of this remains, okay? So what we do is we take our limiting reagent and we're going to convert it to the other reactant that is in excess. So we have all the calculated molar masses that are necessary in this problem. So what we're going to do is this is going to be a very fast step. So we're going to slide this up so that we have some space. Okay. And here we go. So making sure that you know all the previous information there, we're going to start off with the limiting reagent, which is 0.156 grams of Na2O. Okay, and I am going to convert this limiting reagent to the other reactant, which is in excess. That's my first step in figuring out how much of this one in excess remains. Okay, and so I've already done all these calculations of molar masses. So this is 61.98 grams of Na2O. That's equal to 1 mole of Na2O. Here's my vertical stop in between these. Moles of Na2O and moles of FeCl3. Now, I haven't used this mole ratio together here specifically in this problem. We'll just look at our balanced equation to make sure that we got what we want. And that is, I'm going to use a 2 in front of the ferric chloride and a 3 in front of the sodium oxide. That's again coming from our balanced equation. So that is a 2 in front of the ferric chloride and a 3 in front of the sodium oxide. Okay, then we're going to have moles of the ferric chloride, and the molar mass for the ferric chloride was 162.21 grams of FeCl3. This is 1 mole. You should see that grams of sodium oxide cancel out, moles of sodium oxide cancel out, moles of ferric chloride cancel out. I'm going to look at significant figures. I got 3 significant figures, 4 significant figures, infinite, 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 and 5 significant figures. So the fewest number of significant figures I have is 3. So I'm going to plug the following numbers in the following way into my calculator. 0.156 divided by 61.98 times 2 divided by 3 times 162.21. That will equal 0.272 grams of FeCl3. Okay. So now what we need to do is we are going to just take a look at what we have here on this. Okay, how much ferric chloride was used? 0.272 grams of ferric chloride was used. How much ferric chloride do I have? 0.378 grams of ferric chloride. So we're going to move this up right over here, and we're going to say that we have 0.378 grams of ferric chloride, and this is available. This is how much we have. Okay, and how much did we use? 0.272 grams of ferric chloride. This is how much we used. Okay, just making sure that you understand this. Okay, this is the number that's given. This is the number that's calculated. I'm going to take the difference between these two numbers, and I can take the difference between these two numbers because they have the same units and the same formula. When I take the difference here, I'm looking at decimal places. They both have 3, so my answer will have 3. This is 0.106 grams of ferric chloride remain. That is the amount that remains of the ferric chloride that is unreacted within this problem. All right. Hopefully that is looking good for you. It's looking good for me. This is a fantastic problem. I'm going to zoom on out here just so that you can see the whole entire problem in its entirety. I know it might be a little bit small, but maybe you want to see everything all there on one page. There's everything on one page. Take a look at that, make sure that you understand that, just to make sure. We started off with numbers for both reactants. We converted it to the product that had a number so that we can do a percent yield. We took both of the numbers of reactants and we moved them to the product that was asked for, the product that had a value to it. We compared the two numbers here. Since they have the same units and the same formula, we can compare the two numbers. We crossed out the larger number. We kept the smaller number. The smaller number figured out what came of, how did you get this? What is the reactant that made this? And that is Na2O. So therefore, my limiting reagents formula is Na2O. Then my reactant, sorry, the number that is the other one that I crossed out, the reactant of that one is right here, and that one here is right here on this one right here, and that tells you, since this one I crossed out, that reactant is um, uh, the larger one in excess. Then what you do is you take your limiting reagent and convert it to the one in excess. That's what we did right here. We took the limiting reagent, converted it to the one in excess, and that tells you how much is used and required or necessary. Then we take the amount of reactant that you have available to you, subtract the amount that is used or required, and then you get the amount remaining. To get the percent yield, you take the actual value of the product that was given, that's in the numerator, divide by the theoretical or calculated value. Again, the units and the formula are going to be the same, and then you get your percentage. All right. Hopefully that worked for you. A little summary of that explanation of that problem. We got one more problem to do on this worksheet, and then we're done. All right. Again, a quick little advertisement. I'm the Crazy Hat Chemist, and you watching the Crazy Hat Chemist in action. All right. So we're going to zoom on in on this one here, and this is our final problem on this worksheet, and we're going to be really happy once we're done with this. All righty. All right, so let's knock this last problem out. So here we go. It says we have a 0.967 gram piece of scandium metal. Okay, so scandium is an element on the periodic table, and that is going to be Sc. And since that's a metal, it's going to be a solid at room temperature conditions. Is dropped into a beaker containing hydrochloric acid. I don't think this is the first time that we've had hydrochloric acid on one of these worksheets, if not this one. So this is a binary non-metal acid. Hydrogen is a 1+ like all acids have. Chloride is like that. It's a periodic trend charge right there. So hopefully you're comfortable with that. So we have Sc, solid, plus HCl. That's going to be aqueous, like all acids are. Okay, and then we're going to identify the type of reaction. What type of reaction is this? This is a single displacement type of reaction. And how do I know that? I know that because I have an element and a cation-anion combination. Okay, since this element is a metal, excuse me, it's going to displace the either metal or the cation in the California. So we're going to displace the hydrogen, and then we're going to end up with hydrogen. Hydrogen is a diatomic. That's why that 2 right there. And standard state conditions for hydrogen would be it's a gas. All right, fantastic. All right, now we're going to go to our periodic table, find scandium, because we need to know the periodic trend charge on the scandium ion, because the scandium metal is now, once it displaces the hydrogen, will be a scandium ion, and it will combine with the chloride ion. We already know the charge on the chloride ion, and that is a -1 charge. So we're going to go over to our periodic table here. And we have group 1 plus 1, group 2 plus 2, and then we have this next column here, which is in the transition metal region, and that is scandium. It's going to be a 3+. So we're going to have a 1+, 2+, 3+. So what's the charge on the scandium ion? 3+. So we're going to try to combine the scandium 3+ ion with the chloride. That's Sc3+ with that chloride. That will give us scandium chloride. That's SCCl3. Chlorides, bromides, and iodides are soluble except for silver, mercury, or lead, and therefore this is aqueous. All right, so now we have our unbalanced equation there. Now what we need to do is balance it. We always look to find the most complicated formula, or the most unusual formula with the most unusual elements, and that's the scandium chloride. Okay. There are 2 hydrogens and on this side, and then 3 chlorides. So somehow we need to figure out a way to make that work together and mesh, okay? Because the chlorides and the hydrogens are in this same formula. So we're going to find the greatest common factor between 2 and 3, and that is a 6. So that's going to be 6 in front of the hydrochloric acid. Then I'm going to have a 3 in front of the hydrogen. That will be 3 times 2. That will be 6 hydrogens on the product side, yielding those 6 hydrogens on the reactant side. And also, three chlorides here, and I have 6. So therefore, I'm going to have a 2 here in front of the scandium chloride. And then I have 2 scandiums here, and now I will have 2 scandiums on the reactant side. Now I have a balanced chemical equation. Now I can work with this. All right, so now what we have is we have a 0.96 gram piece of scandium metal. I'm going to have one of my monorails with that. So 0.967 gram scandium metal. Okay, and it's I'm going to write this right above this scandium, 0.967 grams. And then I also have 2.93 grams of the hydrochloric acid. Notice that since I have numbers for both of the reactants, that means that this is a limiting reagent problem. Furthermore, I'm going to have to get a percent yield for this because it's one of the questions, but how do I know what to take these two reactants to? I'm going to look at this other number, 1.2 times 10 to the negative 2 grams of gaseous product. What's the gaseous product? That's right there, that hydrogen. This is 1.2 times 10 to the negative 2 grams. That is my actual value when I calculate my percent yield. Okay. Therefore, since I have a mass for one of the reactants and for the other reactant, mass for the scandium metal, mass for hydrochloric acid, and I have a mass value for one of the products, I need to take both reactants to that single product. This problem is very similar to the problem that we just worked out just a moment ago. That is problem number 5. So we're going to be following similar steps, similar process with this. Here's my stopgap between my next step here. So I have grams of scandium needs to go here, and therefore I'm going to use the molar mass of scandium from the periodic table that's in the denominator. That's 44.96 grams. So I'm going to write that right here. That's going to be 44.96 grams of SC. And using my flow chart, hopefully you're comfortable with that now. This will equal 1 mole of scandium. Just like that. I'm going to have my vertical stop. We're going to cross out grams of scandium, grams of scandium. Since this is moles of scandium in the numerator, I'm going to have moles of scandium in the denominator of my next term. That will enable me to cancel out the moles of scandium. And I'm going to go to moles of whatever I want. It just so happens that I want to go to moles of the gaseous product. That would be the hydrogen. So I'm going to have moles of H2 right there. Vertical stop right after this. Now what we're going to do is we're going to use our stoichiometric coefficients from the balanced equation. So I'm going to find scandium, that's going to be a 2, and the hydrogen, that's going to be a 3. Okay. My next term is going to have moles of H2 in the denominator, and I am looking to go for the same units and the same formula of my product, and that's hydrogen, and that's grams. Okay, so this is going to be the molar mass of hydrogen. So that is on my periodic table 1.0079 times 2. So that's 2.0158 grams of H2. That's equal to 1 mole. My moles of hydrogen cancel out, and then I'm going to have a numeric value for this. I'm going to figure out what my significant figures are. I have 3 significant figures here in this numerator term, infinite here, 4 significant figures, infinite, infinite, 5 significant figures, infinite significant figures. In my calculator, I'm going to use the following. 0.967 divided by 44.96 times 3 divided by 2 times 2.0158. Okay, and then I'm going to round that to the fewest number of significant figures, and that will be 3. So my answer here is going to be 0.064 that's grams of hydrogen. And so this is going to be one of my answers that I'll be comparing here in just a moment. Okay. Now what I need to do is I need to take the other reactant's numeric value. That is 2.93. It's units, grams, it's formula, HCl. And I need to take this now to the other, I need to take this to the hydrogen product, like I just did here. Okay, here's my vertical stop in between this and the next term. On this worksheet, I believe on another problem, we've actually calculated the molar mass of hydrochloric acid. So you're going to take one hydrogen, one chlorine. The molar mass for hydrogen is 1.0079. The molar mass for chlorine is 35.453. The number of decimal places in hydrogen is 4. The number of decimal places in chlorine is 3. So I'm going to have my rounded molar mass having 3 decimal places. So that will be 36.461. That's grams, 461 grams of HCl. That's going to equal 1 mole of HCl. Vertical stop in between these two right here, and I'm going to be canceling out my units of grams of HCl. Now I need to take this to the grams of hydrogen, but before I do that, I have to use a mole ratio. That's going to be moles of HCl to moles of the hydrogen. Vertical stop in between these two. And then we're going to use our stoichiometric coefficients from the balanced equation. And so in front of the HCl is a 6. That's why this is a 6. In front of the hydrogen is a 3. That's why that's a 3. I'm going to cancel out my units of moles of HCl. Those are canceling out. Then since I have, sorry for the little paper movement there. I have moles of H2 here. I'm going to have moles of H2 here. I'm going to have 1 mole, and I'm going to have in the numerator the molar mass. And again, we already previously calculated the molar mass. That's right up here in the top term. So 2.0158 grams of H2. This allows me to cancel out the moles of H2. I'm going to look at significant figures at each one of these numbers. There are 3 significant figures, infinite number of significant figures, 5, infinite, infinite, 5, infinite. So I'm going to plug the following numbers into my calculator. 2.93 divided by 36.461 times 3 divided by 6 times 2.0158. And I'm going to get the following number here. That will be 0.0810 grams of H2. And I'm going to circle that. Now what we're going to do, since this is a limiting reagent problem, I'm going to compare these two numbers over here. And that is, they have the same units, they have the same formula, therefore I can compare the two numbers. I'm going to take and compare the two numbers. I'm going to cross out the larger number of the two. Okay, I'm going to keep the smaller number of the two. The smaller number of the two is my theoretical. So this is my theoretical yield. I'm going to figure out from this theoretical yield, the smaller number, what is my limiting reagent? My limiting reagent is the one that made this, which is SC. So scandium is my limiting reagent. The one that I crossed out, the one that might have made this amount, is my in excess element, and that is formula, that is HCl, that's hydrochloric acid. So now I have answered many questions here. I've answered what is my limiting reagent, that's scandium, what is in excess, that's hydrochloric acid, and how much product can be produced, that is 0.0650 grams of H2. Remember, leading zeros don't count for significant figures, but trailing zeros count with a decimal. That's why this has 3 significant figures. I'm going to do the next step here, and that is calculate the percent yield, since this is very close here. Percent yield is the actual over the theoretical times 100. The actual value is given in the problem all the time, and that is 1.2 times 10 to the negative 2 grams of H2 in this particular instance. We're going to divide by the theoretical value. That theoretical value is 0.0650 grams of H2. I'm going to multiply this by 100 because I do want a percentage. Just to make sure, when you are doing the calculation of a percent yield, it's the small number over the large number. It's the actual value, which is given, divided by the theoretical, which is always calculated. They have to have the same units, that is grams in this case. They have to have the same formula. That's H2 in this case. This has two significant figures. This has three significant figures. So once I divide these two, multiply by 100, I'm going to get a rounded number at two significant figures. So it's going to be 18% yield of H2. So there's another one of my answers on this problem. All right, we are almost done. We have one more part to hammer down the nail on this problem here, and then we will be completely done. So we know what reagent is limiting. We know what reagent is in excess. So what we're going to do is we're going to take the reagent that is limiting, convert it to the one that's in excess. Okay, so that is which one is limiting and convert it to in excess. That will give us how much is necessary to react. And again, just like I mentioned on the previous problem here, the previous limiting reagent problem, we've already calculated all the molar masses. So I'm just going to be referring back to all these numbers that we have previously calculated and used. So that will make this monorail train track here go much faster. So again, we're going to start off with the limiting reagent. So I'm going to move this up here just a little bit so you can see most of this here, but without the question. Okay, so we're going to start off with the limiting reagent with the scandium, which is the scandium. So that is 0.967 grams of SC. All right, let's draw our horizontal section here, vertical stop between this step and the next step. This is grams of scandium, therefore this must be grams of scandium. That's 44.96 grams of scandium. That will be equal to 1 mole of the same formula. Vertical stop. Grams of scandium cancel out, so I'm done with that. We're going to have moles of scandium, and then we're going to have moles of the reagent that's in excess, and that is HCl. I'm going to use the stoichiometric coefficients from the balanced equation. So for scandium, it is a 2. That's a 2. For HCl, it's a 6. That's a 6. The moles of scandium cancels out. Vertical stop. Now, 1 mole of HCl, and now we're going to use the molar mass of HCl. And again, that's previously calculated. That's 36.461. 36.461 grams HCl. Canceling out moles of HCl. Looking at significant figures, 3 significant figures, infinite significant figures, 4 significant figures, infinite, 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 and 5 significant figures. So the fewest number of significant figures I have is 3. I'm going to plug this into my calculator in the following way. That is 0.967 divided by 44.96 divided by 2 times 6 times 36.461, and then round that to 3 significant figures. That will equal 2.35, that's 335 grams of HCl. So this is the amount that is required. Okay, so what we're going to do is we're going to look and find out how much did I have originally. How much HCl did I have originally? I'm circling that right here. That's 2.93 grams. How much is required or used? That's what I'm circling right now, 2.35 grams. So I'm going to move this up. Now that you have those in your hand, that's 2.93 grams of HCl is what is available. And 2.35 grams of HCl is required. we're going to take the difference between these two numbers right here, and that will be rounding to the number of decimal places, which is 2, 0.58 grams of HCl is in excess. That is unused. Okay. And that is my last and final answer for this problem. All right. So I'm going to zoom on out on this just so that all of you can see all the parts on this and the whole entire problem here, and just a summary recap of this entire thing. So the first thing that we did is we got a balanced equation here. And then we got our balanced equation. We recognized that it's a single displacement reaction. Then what we did is we wrote down the numbers associated with those formulas from what the question is asking. Looking that we have numbers for 2 of the reactants or both of the reactants, that means it's a limiting reagent problem. Since I have a number for one of the products, that tells me the actual value for my percent yield calculation. I took each of the reactant values and moved them stoichiometrically to the product of which I have given a number for. I compared these two numbers. I crossed out the big one. I circled the smaller one. The smaller one tells me what the limiting reagent is, the one that makes it. That in this case is scandium. This smaller one is also my theoretical value when I use my percent yield calculation. The number that I crossed out, which is larger, the one that potentially could have made that amount but didn't, is my one that's in excess. So that's clearly labeled here. The limiting reagent is scandium. The one in excess is the hydrochloric acid. To obtain my percent yield, I'm taking the actual value, which was given, that's in my numerator, the actual value, divided by my theoretical value, which is always calculated. I'm going to divide them and multiply it by 100. I get my percent yield, another answer. To get the amount that's unreacted in excess, I'm going to take my limiting reagent, and I'm going to convert it to the one in excess. Okay, so that is this step right here, taking the limiting reagent, converting it to in excess. Then I write down how much of that limiting reagent I have available that's given to me in the problem, subtract out the amount that is required or used, and then I have the amount that's in excess that is unused. All right, I think that is a wrap for this entire worksheet. And for this unit. So again, I am the Crazy Hat Chemist, and please subscribe to my YouTube channel, watch my YouTube videos, give me a thumbs up, give me some positive feedback and comments. It makes me want to make more of these videos when you do that. So I greatly appreciate that. Have a great morning, great afternoon, great evening, and we'll see you next time. Bye for now.